Welcome to video 3 in this series. This one's on slope of a curve. We're going to see 3 new vocabulary terms: slope of a curve at a point, tangent line to a curve, and something called the difference quotient. So let's begin. To find the tangent to a curve y equals f of x at some arbitrary point P, notated as a comma f of a, we're going to use the same dynamic procedure as what we did in the previous video, where we had a point P and we picked a point Q, we drew the secant line, but we slowly, with limits, moved Q toward P. So we're going to calculate the slope of that secant line from P to Q. And the way we're going to define Q is going to be P plus a little space. So it's going to be the same x value plus some space h. And then we would calculate the y value by plugging a plus h into the function. And we're going to investigate this as h becomes 0. So as h gets closer and closer to 0, what happens to the slope? In other words, we're going to say the space between P and Q is h, right? So if that limit exists, it is the slope of the curve at P, and we're also going to define the tangent at P to be the line that has that slope. So instead of going to an example or to a new slide with definitions, I thought we would draw this out again graphically. So here is a grid, and we need an arbitrary curve there. Let's call this curve F, and then let's pick a point here, P, and then the value of this, actually, let's redefine that x value to be a. This will be point P, and then its y value would be f of a, so that P is a comma f of a. Perfect. And then we're going to pick a point Q somewhere down the line on the function. And this point Q is going to be defined as h spaces away from our original point A. So this would be an x value of a plus h. So point Q is going to be a plus h comma f of a plus h. And so Q's y value then over here is f of a plus h. Now, as Q goes toward P, that's the idea here. We're thinking about the slope of the secant line through those two, and we're going to move Q towards P. And as we do that, what's happening is H is getting closer and closer to 0. We are moving now, so then A plus H would be here, and then, let's try that again. A plus H would be here, and if we get H smaller and smaller and smaller, eventually what will happen is we will be left with the tangent line and its slope. So let's start this out. How are we going to define the slope between P and Q, the secant slope? It's going to look something like this. I'm going to call it M sec, and it's going to be the y value of Q, which is f of a plus h, minus the y value of P, which is f of a. And then that's going to be over the x value of Q, which is a plus h, minus the x value of P, which is a. And we can simplify that denominator a little bit as f of a plus h minus f of a. And since a minus a is 0, this is just over h. Now, what we want to do with that secant slope is then say, hey, we want h to get closer and closer to 0. So we're going to stick this secant slope into a limit. And that's going to look like this. The limit as h goes to 0 of the slope of the secant, f of a plus h minus f of a, all over h. This should be the slope of the green line over here, the tangent line, because we're moving Q sufficiently close to P to turn the secant line into a tangent line. So let's move from there. Now we get to a formal definition. The slope of the curve y equals f of x at the point a comma f of a is the number m for slope, it's the limit as h goes to 0 of f of a plus h minus f of a all over h, provided that that limit does exist. And then the tangent line to the curve at P is the line through P with this point. All right, it's time for an example. We want to explore what happens with the function 1 over x at some arbitrary point A. And then where does that slope equal negative 1/4? And then answer a little bit about the point A, comma 1 over A for different values. Okay, so let's get going. F of x is 1 over x, and so that means our initial point P might be defined as A, comma 1 over A. All right, next, let's set up the slope. So that slope is going to be the limit as h approaches 0 of this quotient of f of a plus h minus f of a all over h. Okay, so what does that look like? If we plug a plus h into this function, we get 1 over a plus h. So the limit as h goes to 0 of 1 over a plus h minus f of a is 1 over a, and this is all over h. Now, this is going to take some algebra, and in order to simplify this, we need a common denominator. Common denominator is going to be a times a plus h. So we need to multiply by an a here and by an a here. We need to multiply by an a plus h here and an a plus h there. So then my next line of work is going to look something like limit as h goes to 0 of a times 1 is a minus the quantity a plus h. So I'm going to say minus a minus h over the common denominator of a times a plus h. And then rather than divide by h and have another complex fraction, let's just multiply by 1 over h. Okay, so it's starting to look a little simpler. What's happening now? Well, we have a minus a in the numerator, and that goes to 0. That leaves us with negative h on top and an h as a factor on bottom. So that negative h and this h can cancel to leave us with a negative 1. And so that takes us now to our next step, which is the limit as h goes to 0. All that's left in the numerator is negative 1, and all that's left in the denominator is a times a plus h. So as h goes to 0, this quotient becomes 1 or negative 1 over a times a plus 0, or negative 1 over a squared. There's our slope, negative 1 over a squared. So part B, where does this slope equal negative 1/4? Well, it's going to equal negative 1/4 when negative 1 over a squared is equal to negative 1/4. And looking at this, it appears as though if a squared is equal to 4, then we've got it. So it's going to work when a squared is equal to 4, and that means that a is plus or minus 2. So let's think about the original function again. This is going to occur at the point 2 comma 1 over 2, and it's also going to occur at the point negative 2 comma negative 1 over 2. And I graphed this in Desmos so we can check out our answer and see if that's true. So here's the curve. I left bolded in red the 2 points where we said that the line was going to be tangent with a slope of negative 1/4. And here are those lines. Does that appear tangent? Does that appear tangent? Yes, it does. Wonderful. So back to the notes. The last question, what happens to the tangent at the curve at the point a comma 1 over a for different values of a? So let's think about negative 1 over a squared. So as a gets closer and closer to 0 from the right, so that means a is some microscopically small but positive number, then negative 1 over a squared is going to approach, well, negative 1 divided by a positive, really small, tiny number is going to be negative infinity. And then as a goes towards 0 from the left, negative 1 over a squared is going to also again go towards infinity, but this time positive. And so let's see if the graph makes that aware. So yeah, if we can imagine maybe the slope of a tangent line down here, that's going to be almost vertical, which is that infinite slope or undefined kind of slope there, the 1 over 0. So that does seem to match and make sense. So here's one last piece. This expression that we put in our limit. So not the limit itself. So we were looking at this, but just the expression inside, the f of a plus h minus f of a over h, which is a difference of y's over difference of x's, is called the difference quotient of f at a. It's called a difference quotient. We're going to use that phrase a lot in calculus. So we can interpret that difference quotient a couple different ways. If that difference quotient has a limit as h approaches 0, we can interpret it as the secant slope. It's the limit is the slope of both the curve and the tangent to the curve at the point x equals a. So it's a very analytic kind of answer. This represents the slope of the secant as the secant approaches the tangent if the limit as h goes to 0 exists. Or we can also interpret this difference quotient as an average rate of change. Then the limit as h approaches 0 would be the function's instantaneous rate of change at the point x equals 0. So that was the video of slope of a curve. I will join you for the next one, normal to a curve.